Okay, thank you. This is a joint work with my advisor, Gestar Olafsson. So first we define the Fock space. We have the Gaussian measure on Cn by this. Here DC is just the Lebesgue measure, and the Fock space is the intersection of holomorphic functions on Cn with the square integrable functions with respect to the Gaussian measure. This is a reproducing kernel Hilbert space with the reproducing kernel given by kwc equal to e to the wc bar, which we also denote by k sub c. Now the point evaluations are continuous. So by this representation theorem, we have the point evaluation is the inner product with k sub c, the reproducing kernel, and we have the projection operator, which we call the Bergman projection from L2 to F by, again, the inner product with reproducing kernel. Okay, now if we have a essentially bounded function phi, we can define the Toeplitz operator T phi on the Fock space by, first we multiply the Fock space function by phi and we project it back to the Fock space because this is in the L2 space, but not necessarily holomorphic. And the projection is just the inner product with the reproducing kernel, which is given by this integral. So the Toeplitz operator with symbol phi is a bounded operator whose operator norm is less than or equal to the norm of the symbol. Now the C-star algebra generated by all the Toeplitz operators with bounded symbols is not commutative, but we can find subalgebras which are actually commutative. Now, the way we do this, one way to do this is by considering a group action on Cn, and then we can define a group action on the symbol by A dot phi C equal to phi of A inverse C, and we say the symbol phi is G invariant if A dot phi is phi for all the elements A in G. And we denote the space of all G invariant bounded symbols by L infinity C and G, and the corresponding Toeplitz algebra by TG. Now, one of the groups that has been studied over and over again is the unitary group. And so the UN invariant symbols are called radial, they are radial symbols. And it has been shown that the corresponding Toeplitz algebra is commutative. And Rudsky and Vasilevsky diagonalized the radial Toeplitz operators, and the eigenvalue sequences are given by this formula. So they are just sequences on N naught. And Esmeralda and Maximenko showed that the corresponding C-star algebra is isometrically isomorphic to the C-star algebra CBU, which is just bounded functions on N naught, which are uniformly continuous with respect to the square root metric. Now, in our case, we discuss quasi-radial symbols. So to define quasi-radial symbols, we fix a k-tuple n, and we let n be the sum n1 up to nk, and we can identify C in Cn by the tuple C sub 1 up to C sub k, where Cj's are in C and J's, and we define the group G depending on the k-tuple that we fixed to be the product of these unitary groups. And this is again a subgroup of UN, and we have the usual action on the symbols phi of A inverse C, which is also the component-wise actions from elements in UNI. And we consider the symbols which are essentially bounded and G invariant. We call them quasi-radial, and we are interested in the C-star algebra generated by corresponding Toeplitz operators. Now, in this setup, we get two special cases. If we set k is equal to 1, we get the group UN. And if we set k is equal to n, then this is just a k-tuple of ones. So we get separately radial symbols where the group is just Tn. Now, this is a well-known fact. If we have a UN invariant function, so a function is UN invariant if and only if it depends only on the length of C. Likewise, in our case, a function is G invariant if and only if it depends on the length of the corresponding components. Now, to show that the algebra is commutative and to diagonalize the Toeplitz operators, we use representation theory, and we have the regular representation of UN given by phi n of A applied to Fc equal to f of A inverse C, and the Fock space is invariant under the regular representation, but the representation is reducible, and we can decompose the Fock space under irreducible subrepresentations by this direct sum. And here, P, M, C, N are just homogeneous polynomials of degree n. Now, but our group is the product of unitary groups. Our n is n1 plus so on up to nk, and G is un1 times up to unk. And the Fock space FCN can be written as the tensor products of FCNIs. Now we can define the tensor product of each of the representations pi ni corresponding to each group uni to be this. So it's just the tensor product of pi ni a1 so on. And so again, this representation is reducible, and we can decompose FCN under irreducible subrepresentations like this. Now PMI, so the invariant subspaces are the tensor products of homogeneous polynomials. Now we also have the quasi-radial Toeplitz operators intertwines with the representation for all quasi-radial symbols. So by Schu's lemma, Toeplitz operator acts as constant times identity on the invariant subspaces. Now also the decomposition of the representation into irreducible subrepresentations is multiplicity free. The subrepresentations are not equivalent. So since G is a compact group, we have that the intertwining operators are commutative, and we also have that Toeplitz operators intertwines with the representation. So the Toeplitz algebra is commutative. Now what's left is to compute the constants gamma NA. Now it's given by this formula. So the one here is just a k-tuple of ones. N plus m minus 1 factorial is understood in the usual sense. R to the n plus m minus 1 is also understood in the usual sense. And square root of r is just taking square root on each of the components. Now, so to prove this, we just used polar coordinates appropriately and the homogeneity of the polynomials. And one thing we can notice is, so when n is equal to the k-tuple of ones, we get the separately radial case. So these two cancels. So we have 1 over m factorial. Here we have m. So gamma NA is just an n minus 1 left shift of gamma 1A. This actually helped us simplify our proofs a lot. Okay. And now we discuss the C-star algebra. generated by the corresponding Toeplitz operators. So we start by defining the square root metric rho k. It's given by this formula. And CBU is just bounded functions on n naught k, which are uniformly continuous with respect to the rho k. And we have that the set of all eigenvalue functions that we defined previously is in this C-star algebra. And so earlier, we noticed that gamma NA is a shift of gamma 1A. Now, if we look at this metric, to make this metric really small, we have to make mi's and mi primes really large. So if we shift a sequence in CBU, it doesn't matter, it's still going to be in the same C-star algebra. So this C-star algebra is invariant under left shifts and right shifts. So the question boils down to just the separately radial case. And we actually proved that the set of all eigenvalue functions Gn is a dense subset of CBU n naught k rho k, but the only thing that we have to prove is G1 is a dense subset in here. Now, from this, it follows that the Toeplitz algebra is isometrically isometric to the C-star algebra CBU. Okay. Now, to prove that the set of all eigenvalue functions is a dense subset, the first step is to prove this proposition. So if we have an element sigma in CBU, and if epsilon is greater than 0, then there exists a symbol A and an integer n such that for all m with all the components greater than 1, we have the control. Now we can rewrite this in this way. If we define the set Kn to be things in n naught k such that at least one of the mi's is less than or equal to n, then this can be rewritten as sigma minus gamma 1a restricted to Kn complement sup norm is less than epsilon. Okay, now if k is equal to 2, the picture is like this. We have Kn complement here and Kn would be this set. Now, if I just look at gamma 1 a plus b, a sum of two symbols, I can write gamma 1 a plus b as gamma 1 a plus gamma 1 b, and I can break down gamma 1 a as gamma 1 a restricted to Kn and restricted to Kn complement. And then just by applying triangle inequality, I get this bound. And so from the previous proposition, we get control over this part. So what's left is to control this part. Now, but we do this, we do not, so we actually prove it as an inductive step. So we assume G1k minus 1, I mean, so the set of eigenvalues when for k minus 1 is dense in CBU n naught k minus 1, rho k minus 1. And then if sigma is in CBU n naught k, and if epsilon is greater than 0, then there exists a symbol such that we can control this part. Now, from this, it follows that G1 is dense in CBU because the case k is equal to 1 was proved by Esmeralda and Maximenko. Then using the previous inequality, we get the proof of the proposition by induction on k. Now, to prove the proposition, this proposition. So we need, we need, given epsilon and sigma in CBU, we need to find n and a such that we have control for when m is in Kn complement. Now we follow 3 steps. So the first step, we extend sigma to CBU on R plus K. So sigma is on N naught K, but we extend it to R plus K such that, preserving the subnorm of sigma. And then we define the function g by g of x equal to sigma tilde of x squared. And this gives us a function in which is bounded and uniformly continuous in the usual sense. And we also have that if we consider the heat kernel, when we convolve heat kernel with bounded functions, this set is a dense subset of bounded uniformly continuous functions in the usual sense. So we get a candidate B from this. So we can say that there exists B such that H star B minus G subnorm is less than epsilon over 3. And now then what we do is we restrict the function B in to R plus K, and we also have control H star A minus H star B is less than epsilon over 3 when xi is bigger than n1 for all case. And then, so the reason that we follow this method is because we can approximate the eigenvalue functions by convolutions with the heat kernel. This is just a property of the kernel of the integral involved here. And then we just put these 3 inequalities together and we get the proposition. So actually I thought I would take more time than I took, so that's all I prepared.